Hey everyone, welcome to the Foundry by Forge College. I'm super excited you're joining us for this explainer today. We are diving right into the next major piece of our Advanced Solana Concepts track. So in our last lesson, Anatomy of Cloudbreak's data structure, we unpacked how logical mapping is totally separated from physical storage. But that immediately brings up this massive, literally game-changing operational question. Okay, you know exactly where your data lives, and you know how to look it up. But how do you actually divide it up so that those lookups and storage operations scale predictably when the system is just getting absolutely hammered by heavy load? Well, that's exactly what we're going to figure out today as we explore Cloudbreak data partitioning strategies.
Right, so here is the core problem we've got to solve. How do we split data without completely breaking the system? Because think about it, when you're dealing with thousands of concurrent operations, you simply can't just throw everything into one giant bucket. And honestly, you can't just randomly slice it up without a plan either. That's a recipe for disaster. We need a bulletproof strategy to make sure the system stays lightning fast, super stable, and crucially, highly parallel.
So here's our engineering blueprint for this explainer. We are going to look at the partitioning problem, check out the plates model, break down 3 big strategies, dive into boundary management, and then finish up with some essential stability rules. Let's get right into it.
All right, Section 1, the partitioning problem. Subtitle here being distribution versus locality.
Moving on to Section 2, the plates and dishes model. We're going to use a quick kitchen analogy here.
To really picture that tug of war between distribution and locality, I want you to imagine a wildly busy, totally chaotic restaurant kitchen. Think of a partition as a plate moving down a conveyor belt. The dishes getting put on that plate, those are your data keys. And the chefs frantically trying to place those dishes, yep, those are your concurrent threads. Now, if your plates are tiny, your kitchen staff is going to have this massive tracking overhead just figuring out what goes where. But on the flip side, if your plates are gigantic, they're painfully slow to move down the line. So it's a constant balancing act. You have to find that absolute perfect plate size.
Which brings us to Section 3, 3 big strategies. Specifically, hash, range, and key-based partitioning algorithms.
So how do we actually decide which dishes go on which plates? Well, let's look at the 2 absolute heavyweights first, hash-based versus range-based partitioning. Hash-based partitioning takes a key, runs it through a math function, and boom, it spits out a partition ID. This is literally fantastic for even load distribution. If you've got millions of small uniform writes, like random public keys, hashing spreads them out flawlessly across all your plates. But there is a catch. It has terrible locality. Your related dishes get scattered everywhere. Range-based partitioning, on the other hand, is the exact opposite. It groups contiguous keys together. If you need to do sequential scans or read a ledger in order, range is your best friend, because all the related dishes are sitting on the exact same plate. But you really got to watch out, because if one specific range suddenly gets a ton of traffic, you end up with a massive hotspot. It's like 100 chefs suddenly fighting over one single plate. Not great.
And then we have key-based partitioning. Some people call it directory-style partitioning. This approach groups keys by a logical application attribute, something like a tenant ID. Going back to our kitchen, this is basically like telling your chefs, hey guys, all the spicy dishes, they always go to this specific dedicated corner plate. It's actually a pretty brilliant hybrid approach. It preserves semantic application-level locality while still keeping the rest of the system safely distributed. Okay, comparing them directly really highlights the trade-offs. Hash gives you great parallelism, but poor locality. Range gives you amazing scan speeds, but you risk those nasty hotspots. And key-based gives you great semantic grouping, but it definitely requires careful monitoring to avoid imbalances. There is rarely just one perfect magic bullet answer in systems engineering. There's only the right answer for your specific workload. And honestly, analyzing trade-offs exactly like this is a huge focus of the learning programs we build at Forge College.
All right. Let's shift gears from theory to operations. Section 4, boundary management, splitting and versioning.
So what actually happens when one of those plates gets completely, hopelessly overloaded with dishes? Well, Cloudbreak executes this really precise 3-step dance to split the plate without dropping any food. Step 1, the system quietly creates a brand new partition and just starts copying data over in the background. Step 2, it installs an in-progress metadata version. This basically tells the clients and the chefs, hey, we're moving some stuff around, so route your writes to both plates for a second or talk to a coordinator. And finally, Step 3, only after a final, absolutely perfect synchronization does the system flip the metadata to mark the split as complete. This is super important because it guarantees that readers and writers never ever lose data or see corrupted states during the transition. Now, to manage all those transitions smoothly, Cloudbreak relies on a concept called epicid metadata. Think of an epic as a tiny integer version sticker slapped right on the side of our partition plate.
Clients read this sticker and they cache it. They only stop to ask for directions or download a new map when they try to place a dish and suddenly get a mismatched epic error. This is just a wonderfully elegant solution because it drastically reduces the network chatter and the lookup overhead of constantly having to ask the system, hey, have the plates moved yet? Moving on to our final section, Section 5, Stability Rules, Keeping the Kitchen Calm.
Listen, splitting plates constantly is absolutely exhausting for the system, so we rely on a few practical heuristics to keep things stable and prevent what we call metadata churn. First up, you want to avoid splitting partitions just because of a short temporary spike in traffic. Don't panic split. Second, enforce a minimum partition age, just so the plates have time to settle down. Third, you should really base your splitting logic on sustained load thresholds over time, not just instantaneous snapshots. And finally, if you run into a massive hotkey issue, say one single account is generating an absolute frenzy of activity, don't keep splitting the partition into smaller and smaller pieces. That's a trap. Instead, handle that specific hotkey via dedicated replication or rate limiting. These rules of thumb are absolutely crucial for keeping your metadata footprint manageable, even under intense operational stress.
So I want to leave you with this final kind of provocative thought. How will your specific workload access patterns shape the way you design your partitions? It's like a giant puzzle. In our next lesson, we are going to challenge you to take these exact concepts and apply them to real-world traces. You'll actually map incoming operation patterns to partition map entries and see all this kitchen chaos in action. Until then, make sure you head over to forge.college to dive deeper into this subject and explore our massive library of other Web3 educational resources. Thank you so much for hanging out with me on this explainer, and I will see you in the next one.